Hello and welcome to section 14.4 on triple integrals. In this intro video, we're just going to help motivate what triple integrals can do for us, and then we'll go ahead and state their definition. Okay, so to start, let's suppose we have some region in three-dimensional space. So E here is a region in R3, and let's suppose our function f tells us the mass density at a point x, y, and z within our region. And just to be specific, we'll say that density is measured in grams per cubic centimeter. Okay, so as we vary through this solid blob, okay, our function f is just telling us the density, the mass density at these various points within our blob. And if I wanted to say measure the total mass of the blob, well, I could go ahead and partition the region into a bunch of smaller regions. Okay, this is just like what we did for double integrals. And now I'll go ahead and say that for each one of these little regions, the width is delta x, the length is delta y, the height is delta z, and so the volume of this little box would be what we'll call delta v, and that's just the product of each of these small changes in x, y, and z. Okay, then we'll go ahead and choose a point within each one of these little boxes, and we'll call this a sample point, just like we did for double integrals. So xi star, yj star, zk star. And if I go ahead and look at the following products, so in other words, take your function f and evaluate it at your sample point. So this is going to tell us the mass density at this sample point, and if I multiply that by the volume of the box, well, density times volume is just going to give us an approximation to the mass of this little box. And then if I go ahead and add up the masses of all the little boxes, that's going to give me an approximation to the total mass. And then we just observe that our approximation gets better and better as we let the number of partitions grow, and so that's naturally then going to lead us to the following limit definition of the triple integral. Okay, and you notice here we have a triple sum, and that's because we're summing now over the x direction, y direction, and z direction. And you can also see that's reflected in the integral notation. We now have three integral symbols right here on the left, and of course this is not going to be the approach or the method we'll use to actually compute this. Okay, we'll look at iterated integrals much the same way we did for double integrals. Okay, I do want to highlight that again, as we set up here, in the special instance when your function f is, say, a mass density, then the total mass is given by this triple integral. Okay, and this is a really common use of one of these triple integrals. Okay, so we typically don't think of our function f as denoting some kind of height like we did for a double integral. You usually think about your integrand as some kind of density function, whether it's, say, mass density or charge density. Okay, and so when you multiply your density function by your change in volume, this is just going to give you the stuff that you're measuring, so say mass or charge. Okay, and then this integral here is telling you now sum, say, the mass as you vary over this region. Okay, or sum all the charge as you vary over this region. Okay, that's typically the interpretation there. Okay, and so the last thing I'm going to say here is, yeah, we're not going to use that limit definition to actually compute these things. So in the special case when our region E is a solid box, so I've just labeled, say, the bounds here, A, B, C, D. I don't want to use EF because F's already taken and E is reserved for Euler's constant, so say GH. If this is a solid box, then we can compute this triple integral as an iterated integral. And I just wrote down the specific integral in the order dx, dy, dz. But there is a Fubini theorem that says that all the various triple integrals you could create, and if you give this some thought, there's actually 6 of them because there are 3 variables now, x, y, and z, that you can permute around. But this Fubini theorem says that all 6 of those iterated integrals are equal, and they're equal to this triple integral. Okay, so in the next video, we'll look at computing one of these things. All right, thank you.